Physics Week 7 CA. Which component can be used together to experimentally measure the gravitational acceleration? So we can use a ticker timer. A ticker timer is like, for example, you have a paper and you have a machine here that every 1 second it punches a hole into it, and you have a weight here. So when the weight falls, every 1 second it will punch a hole in the paper, for example. So we can use that to measure gravitational acceleration. Or and an electronic stop clock, because human reaction time is a bit late. An electronic stop clock to measure the exact time. And strobe photograph, it's like this big thing. An object falls down into it, and also each time it measures it, each 1 second, for example. We can tell also the gravitational acceleration from it. A spring balance, no, we don't need a spring balance or a speedometer. A body is free falling near the surface of the earth. What can be said about the body's acceleration? When a body is free falling, any body free falling, its acceleration stays constant at 9.8. Whenever anything's free falling, the acceleration stays constant. A 5 kilogram box is placed on a table. Select the equation that relates the mass m of an object to its weight w. Now we know that F equals ma. Now we can change this equation to put F is weight and m A can be g, gravitational acceleration, mass stays mass, and F becomes w for weight. So we get w equals mg, and that's how we find weight. Knowing that the gravitational field of strength is 9.8, what is the weight of the box? W equals mg, m is 5, and gravitational acceleration is 9.8. You can put it into your calculator, and you get exactly 49. A skydiver is shown below. Describe the motion of the skydiver in chronological order, or label the first step as 1. So first, when the skydiver, he first needs to jump into from his airplane without opening the parachute until he reaches terminal velocity, and then he opens up his parachute, and he'll keep slowing down and falling until he also reaches terminal velocity again. So 1 is the skydiver jumps from the airplane without opening his parachute. 2, the skydiver speeds up until he reaches terminal velocity. 3, the skydiver opens his parachute and starts slowing down. And 4, the skydiver's speed decreases until he reaches terminal velocity. A 1200 kilogram car initially traveling at 25 meters per second stops in 5 seconds once the brakes are applied. What is the magnitude of the average force applied by the brake? Now they want the force, F equals ma. We have m, we want to get a. We can use the equation V final equals AT plus V initial. For VF, we want to find that. It stops, becomes 0. A is A, we need to find that, times 5 seconds plus V initial is 25. We move to the other side, minus 25 equals 5A, divided by 5 minus 5 equals A. Now we don't need to use the minus here, the minus just tells us that the force is acting in the negative direction, or the object is decelerating. We have the acceleration now, it's 5 times the mass is 1200 equals F, and F is 6,000 newtons. What would the net force acting on the car be if it moves uniformly? Now, when they say moves uniformly or stays at rest, the net force is always zero because of Newton's third law, I think, one of Newton's law. Yeah. The gravitational force between two masses that are d meters apart is F newtons. If the distance between the objects become 2d, what is the force between the masses will become 0. Blank F. We know that we have Fg equals G m1 times m2 over distance squared. We got that from Newton's law of gravitation, or Newton's fourth law. So we have d squared, and the distance then becomes 2d squared. That becomes g m1 m2 over 4d squared. So we divide that answer by 4, so it becomes 0.25 F. 1 divided by 4 is 0.25. Here they say a motorcycle of mass 300 kilograms is moving along a straight track with velocity 40 meters per second. When the rider hits the brakes, a resisting force of magnitude 2 kilonewtons is applied. Neglect the air drag. Here they want us to get the time. We first need to get the acceleration with F equals ma. F here is 2 kilonewtons, 2000 newtons equals 300 times x. We get 2000 over 300 equals x. We can cancel the zeros, so it becomes 20 over 3 equals a. Now we use the other equation that we used in the other question, v final equals at plus v initial. Now we have that it hits the brakes. The v final will be 0 equals at is 20 over 3 plus v initial is 40. Now we want to find the time, so we put the time, and the object is decelerating, so we put the minus. So we move the force to the other side. It's minus 40 equals minus 20 over 3 t. We then minus 40 divided by minus 20 over 3 equals t. KCF minus 40 times 3 over 20 minus. We cancel, and the minuses cancel كمان, 6 equals t, 6 seconds. For this question, a box is pulled with force F on a rough inclined, making an angle 30 degrees with the horizontal as shown below. The box moves with a constant speed. Again, we said that constant speed means that the net force is 0. So since the force is 0, the acceleration is also 0, because a is F over m, 0 divided by anything. Anyways, when the moving at a constant speed means that the acceleration is 0. It doesn't accelerate because no force is applied onto it. The box is said to be in equilibrium. You have to memorize equilibrium. And the behavior of the box is predicted by the principle of inertia from Newton's third law, or from Newton's first law, the principle of inertia. A box of mass 3 kilograms is pushed on a rough surface with a force of 8 newtons, as shown below. The resistive forces opposing the motion of the box is 2 newtons. فهي these two forces are acting in opposite directions and equal magnitude, they can cancel each other. وبعدين F8 minus F2 is 6, 6 equals MA. Mass is 3. They want the horizontal acceleration first. We have the horizontal forces. 6 divided by 3 equals A, and A is 2 meters per second squared. Now here in the other part they want the vertical component of acceleration. But when we go to the vertical forces, they cancelled each other out. On the vertical axis, the object doesn't accelerate. Which statements are true about the acceleration of gravity? Now we know gravity is directed vertically downward because an object falls down. It is the acceleration at which all objects free fall towards Earth. Also, yeah, that's the definition of gravity, of gravitational force. It varies depending on the mass of the object. No, it doesn't, because on Earth any object falls down with 9.8 meters per second squared. It can be measured using a ticker timer, yes, as we saw in the previous question. The unit of acceleration due to gravity is Newton per times kilogram. No, it's not. It's W equals mg. So it's it's W over m. So the unit of it is N per kilograms. The gravitational field strength of Earth is the force per unit mass at which the Earth pulls all objects downwards. You have to memorize this definition. Gravitational field strength is the force, and it pulls objects downwards towards the center of the Earth. The acceleration due to gravity is the same as the gravitational field of strength. Acceleration due to gravity and gravitational field of strength are the same thing. We saw from the previous question that the gravitational field strength is the force per unit mass at which the object pulls, at which the Earth pulls all objects downward, and acceleration due to gravity is the same thing. So drag and drop the mathematical expression of Newton's universal law of gravitation. Newton's first law of gravitation, it says that if the gravitational force is directly proportional, so we need a proportionality constant G, for example, is directly proportional to the product of its masses and inversely proportional to the square of the distance. So if you know the equation or you know the law, you can get the other one very easily. Or here is the distance. Which statements about gravitational acceleration G are true? Its magnitude decreases with altitude. Yes, because the more you go up, the further the distance between you and the core of the Earth. So the weaker the force dragging you to the center of the Earth. It becomes equal to 0 when the distance becomes greater than the radius of the Earth. You need to know this. Gravitational force is never zero. It's never zero. There is always some kind of force. It may be so weak that you can't notice it, but it's never zero. It is practically constant over the few hundred meters above sea level. Yeah, it is. When you first go up a bit, you don't notice it much, but when you go a lot up, you notice it. Its magnitude increases as the mass of the planet decreases. No, it doesn't. No, it doesn't. We have the equation m1 m2 g over d squared. So the more the mass goes up, the more the gravity goes up. its magnitude increases with with altitude? No, it doesn't. We just explained why it decreases with altitude. A particle is at a distance r from planet A of mass m and gravitational field strength Ga as shown below. The same particle is then placed at an equal distance r from planet B of mass m and gravitational strength Gb. They want us to find the gravitational attraction at big M equals to small m if capital M equals to 2m and if m is 0.5 small m. So again we have the Fg equals to G m1 m2 over d squared or r squared. We can then do that if m1 is m2, the gravitational field stays the same, it doesn't change. And if m is equal to 2m, we get 2m1 times m2 for 2m1 m2 for the gravitational field of A, which is m, is double that of m, so it's double of the gravitational field of B. And if m is 0.5 small m, 0.5 small m, so we have m times 0.5 m2, we do 0.5 m times m2, we get that Ga is half of Gb because it's half the mass. We get Ga is equal to 2Gb. The gravitational field strength in deep space can be considered, you can say 0 negligible, null, 0 equal to 0. You can say all of that, but when you're in space, you can't feel the gravitational attraction because you're so far away. So it's negligible or 0. A satellite is an object drifting in space around a planet. What force makes a satellite orbit around space? Now we took that the weight of a satellite is not negligible. There has to be a force acting on it to keep spinning. Now we also know that it spins around a planet or star in an orbit, and we also know that it keeps falling down no matter what. It keeps falling down as it moves. It falls down, but it never reaches the surface because of the force, the initial force pushing it. It keeps falling down. So the force makes the satellite orbit around the planet its weight. According to Newton's first law, what would the trajectory of satellite if no force is acting on it? If there is no weight acting on it, if we said that its weight is negligible, instead of falling down in a curve, it will just continue in a straight line and will never stop because there's no force stopping it. Astronauts inside a space station feel weightless. Yeah, they feel weightless, but they aren't actually weightless, but they only feel weightless. Which statements about terminal velocity are true? Select all that applies. If the velocity acquired when the net force on the body becomes zero. When the body falls down, it meets air resistance. So say for example a body free falls with its weight 5 newtons. Since it's free falling, some air resistance will be here, and it reaches terminal velocity when the air resistance equals to the weight. It keeps falling down with a constant velocity because the forces on it cancel. It has a zero net force. When the net force on the body becomes zero, it is related to air resistance that increases with speed. Yeah. It is larger when the surface area of an object is large. When we're talking about terminal velocity, the more the area of an object, the more air resistance it gathers, the slower it goes down, the slower the terminal velocity. It is only acquired by objects sliding down a smooth surface. No, it doesn't. No, it's not. It is a constant velocity. Yeah, it is. Racing car bodies have aerodynamic shapes in order to reduce air resistance. When they say aerodynamic shapes, it's most of the time it's just to reduce air resistance. That's it. A bucket of mass 2 kilograms is being lifted vertically by a rope. The bucket accelerates at a rate of 1 meter per second. Use G is 10. The weight of the bucket is, we know W equals mg. We want W, and we have m is 2, and G is 10. So W is 20 newtons. The tension in the rope is there is an equation for tension, mg plus ma equals tension, or T. So we have mg, the weight, is equal to 20, plus the mass is 2, and the acceleration is 1. So T equals 20 plus 2, and T is 22. A constant force F1 of magnitude 10 newtons is applied to block A of mass 1.0 kilograms, which pushes against block B of mass 4.0 kilograms. The block slides over a frictionless surface. عشان it's frictionless, there is no other force acting on it, so we just use F. A is 1 and B is 4. The acceleration of the blocks, they want all of the blocks, so we add the mass of it, it's 5. We get F equals ma. We have F is 10, m is 5, and a is 10 over 5 is a, so 2 is a. You can say 2.0. They don't really care about significant figures as much in physics as they do in chemistry, but it's better to put it to the right amount of significant figures. The force AB acting on block B by block A is blank newtons. So we have the acceleration, and they only want it on block B. So F equals ma. M is 4, A is 2, so the F is 8. Again, they also accepted 8.0, but it's also better to put it to the amount of significant figures. The diagram below shows 3 forces acting on an object. So we have F1 is going up, F2 is to the left, and F3 to the downwards. This force doesn't have anything on the other side, so it doesn't cancel, it stays the same. This force is going down, this force is going up in opposite directions, so this force cancels, and a bit of this force cancels. We still have a bit remaining from this one. Now we only have force 2 and force 3 dash. These two are perpendicular, so the F resultant will be the hypotenuse of it, like this one, Fa. In this question, they want us to complete Newton's universal law of gravitation. We know that every two particles, G, have the gravitational field directly proportional to proportionality constant G, directly proportional to the product of their masses, and inversely proportional to the square of the distance. For every two particles of matter in the universe attract each other with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance. A 60 kilogram skydiver is free falling in mid-air. After a certain interval of time, he reaches a constant speed. Take G is 10 meters per second squared. Now here, they are asking what is the term to represent the speed that the skydiver reached. Now we know that it's constant speed while free falling. We also said that when it's a constant speed while free falling, So the matter has reached terminal velocity. So the term here is terminal velocity. And then they want what is the net force acting on the skydiver once he reaches that speed. We also said whenever it's terminal velocity, the net force acting on the object is zero. The air resistance cancels out the weight of the body. What is the magnitude of air resistance at that moment of time? So since the air resistance in terminal velocity cancels out the weight, and here the weight is W equals mg. M is 60, G is 10. We get W is 600 newtons. So he's falling down with weight 600 newtons, and we want the air resistance to cancel that with a net force of 0. So it's also 600 newtons.